I want to review electron scattering in the context of getting ready for diffraction. And how many of you know Bragg's law? How many of you have heard of Bragg's law? Okay, so those of you who don't remember what it is, at least have heard about it. Because we're going to kind of review a little bit of diffraction. We're going to need it for the pixel array detector and for the imaging 2D materials that we're going to do this afternoon. The other one I want to give you a sense of in this lecture is what happens when the scattering in the crystal is quite strong because the crystal is thick. Don't sit over there because I'm not going to be able to see the board over there.
Oh, sit here?
Right. So a couple of concepts I want to review that we're going to need. Robbie started out the summer school with a diagram very close to this one. The lens, right? And the things that you did with the lens as in high school is the whole point of a lens is it maps you from the object plane to the image plane, and it's a one-to-one mapping. Occasionally you hear people doing X-ray diffraction experiments where they say, I got 1 angstrom resolution with my X-ray diffraction experiment. The answer is no, they didn't, because X-ray diffraction is a many-to-one mapping. It's like you took the face of every person in the room and you reconstructed the average face of everyone in the room averaged together at very high spatial resolution, and you very precisely measured where their teeth were on average. And that's impressive, but it's still not solving for each one of you as an individual. And that's the whole point of electron microscopy, is it's one-to-one. Now, the point of the image is this point over here is all the rays that went at all different angles, but that started from this point, end up at that point. And of course, if I know where my back focal plane is and I know where my image plane is with respect to the focal plane, I know the magnification of the lens. And that's the stuff, you know, that you did, one on image and one on object and one on F, and that stuff that you did in geometric optics. So here's another point in the image, and all the rays from that point end up there. Now the thing that Robbie pointed out in the beginning was all rays that travel parallel to the optic axis go through the center of the back focal plane. And when we start to think about scattering physics, the way you can kind of think of that was, right, I have my object over here. I had an initial ray over here with momentum p, which is a vector. And I'm going to, a little later on, I'm going to deal with waves, so I can write P is h bar k, k is the wave vector. And it scatters, and if it continued on in a straight direction, so here is P prime, is h bar k prime. If it went on straight, unscattered, that would be the forward direction. And that would have corresponded to rays. So this is an object that, imagine I illuminate my object back over here with a parallel beam of electrons. Parallel beam of electron comes in, it hits the object. Those rays that traveled in the forward direction over here did not deflect. They're going to end up going through the center of the back focal plane. So the way to read off the back focal plane is if anything appears in the center of the back focal plane, that's the unscattered beam, or at least it's the forward scattered beam, because the beam is allowed to pick up a phase shift as it goes through the sample even without changing direction. And then the way you construct where the image is, of course, is you draw a straight line through the center of the lens. Any ray that passes through the center of the lens is not deflected. Rays that pass further off from the center of the lens, you can see, are deflected more. Right? This one went totally straight. That one bent a little bit. That one bent a lot. Now, what about the rays that did not travel parallel to the optic axis? They end up, they have to go back to the same point in the image plane that they originated from in the object plane, because all the intensity is a one-to-one mapping. But they took a path that had a different direction, and so they did not go through the center of the back focal plane. So here's a ray that was scattered at an angle, and that might well have done this, and so it went through some angle theta. Let's call this one again, P prime is H bar K prime, and then this one is unscattered, so this is just P is H bar K. Right. The momentum transfer, P before, P after, right? Momentum transfer Q, P prime minus P, back to Q over there. This is basically, even though I've got it written down as an angle, this is going to be measuring momentum transfer Q. Now, if I had another ray at a different position in space, but it's scattered through exactly the same angle, you can see that it ended up at the same point in the back focal plane. So the beautiful thing about the back focal plane is it separates things out by angle, and because of this triangle over here, the angle is related to Q. So we have this nice relationship in this little triangle here that this vector Q is related to the angle, just because it's a triangle and you know what the angles inside a triangle are. And we'll come back and we'll draw that out a little bit nicely, but you can certainly see that if I turn this into a right angle triangle, then sine theta over 2 is going to be a Q over 2, and then the length of this thing is going to be, sorry, I should call this H bar. H bar Q equals that, because what I really want to write down, Q is equal to K prime minus K. I'm just going to drop my H bars. And that is my scattering geometry, and so my Q is related to sine theta, the angle. So what happens in electron microscopes is, if I'm thinking of geometric optics, I keep talking in terms of angles, but all I have to do is remember this triangle, and I can very quickly turn my angle back into a momentum transfer. So the important thing about the back focal plane of the lens is its momentum space. Right? And if you think about it, if I'm looking at wave vectors K, a wave number has the units, a wave number is 2 pi over lambda from your wave optics class. Wave numbers have the units of inverse angstroms, and position has the units of angstroms, because that's kind of the natural units to work with for electron microscopes. So the way to think of what happened in the back focal plane is you're all very much used to spatial frequency, to time frequencies, right? So you're used to, I have a wave with a period of a second, and then that wave has a frequency of 1 hertz, right? So spatial frequencies are like time frequencies, except they're in space and not in time. So you know that when I go from time to frequency, I did a Fourier transform. When I go from space, real space, to the back focal plane, I have done a Fourier transform. I'm in reciprocal space because I'm in inverse angstroms, and that's the wave number space, and put an H bar in front of that, it's momentum space. So this back focal plane of the microscope, if I happen to put my detector in the back focal plane, I have a momentum resolved detector. And we're going to come back to that in the second lecture, and we're going to use momentum resolved detectors to measure probability current flow. What I want you to remember for now is the microscope has a very convenient way of doing Fourier transforms for us, which is just simply switching to diffraction mode, and you get to see the square of the Fourier transform, because remember, when I look at a wave function, I don't see the wave function, I see psi squared and not psi. So there I am reminding you that everything at the same angle ends up at the same place, and that's sort of the geometric construction of a Fourier transform. We're going to talk in a little bit about, well, what happens if I only let the rays at that angle go through and form an image, and we'll think about that. What I want to set up is what Robbie brought out in the first lecture. Typically, when we do diffraction, your starting point is a parallel beam comes in, it scatters off a point object, and scattering from a point object sends out an outgoing spherical wave. And the outgoing spherical wave, a plane wave is e to the I kr, an outgoing spherical wave, because the wave, as it gets bigger, I spread out my intensity over a bigger and bigger circle, it drops off as 1 on r. Huygens principle is that any arbitrary wavefront is just an infinite sum of spherical wavelets that you integrate over, and you add up all their little outgoing spherical waves in phase to get the actual shape that you want. And a wavefront is a line of constant phase, so it's all the lines of, say, 0 phase or pi phase. So the result is, if I have some object and I send a parallel beam through the object, each point in the object produces an outgoing spherical wave, and then I have to coherently add up all those outgoing spherical waves in phase when I come out to an object that's far away. So here we are, the object, the wave went through the object. This is a convolution of my initial wave function, whatever it may be, with some function that's describing the scattering at every point in the object. In this case, it's 0 out there and 1 everywhere in that region. And at every point in that object, I produce an outgoing spherical wave. So the diffraction through the aperture is the outgoing spherical wave generated with a particular intensity at that point in the object and essentially convolved with my incident wave function. Right? So just a convolution of outgoing spherical waves with the object you happen to scatter from. And because the outgoing spherical wave has an e to the I kr stuck up there, this has the effect of performing a Fourier transform. Right? This is a Fourier transform over a limited field of aperture. In the far field, I get to expand out this expression. That's the reason why I wasn't worrying about the 1 over r, is because in the far field, this distance r is enormous compared to r prime, the object. Right? R is infinity, this is finite. I basically don't worry about the r prime term at all. It's essentially constant on the bottom. It's just 1 over r, which is how far away I am. And when I simplify it that way, my outgoing wave is the Fourier transform of whatever the object was. And if this was a plane wave to come in, this is particularly simple. It's just the Fourier transform of that object. So here we are. This is the far field. So what I'm looking at is things as a function of momentum transfer as a function of angle, and it's just mathematically the Fourier transform of the object that was there. So that's just kind of setting up the math for what I sketched out with ray diagrams in the previous slide. As I told you, the wave number k, and then there's a little note down over here. Crystallographers use k as 1 over distance. Physicists use k as 2 pi over distance. It's a confusion, and the reason for that is it's where do you put your 2 pi's in the Fourier transform. So crystallography, you put the 2 pi up in the exponent. Physicists would have a 1 over root 2 pi stuck out the front for normalization. Physicists hate 2 pi's up there because physicists take derivatives and then you bring down extra factors of 2 pi all over the place. And it gets very, very messy in writing out elegant derivations and then making dimensional arguments. Crystallographers, on the other hand, don't really do a lot of math, but what they do a lot is Fourier transform in their heads. And the beautiful thing about the crystallography definition of k equals 1 over d is Bragg's law is basically 1 over d is your k vector. You don't have to worry about funny 2 pi's. So when you look at crystallography inverse angstroms, you just read it off as 1 over angstroms, and if it says You know, 0.5 inverse angstroms, that means a 2 angstrom lattice spacing. If it was the physics notation and it said 0.5, I'd go, well, that's 2 times 2 pi is 12, and I've got to remember to divide or multiply, and you get in a mess. So crystallographers are very practical, but they don't expect to do algebra. The thing I'm kind of pointing up over here is my wave vector k is a vector because there's kx and ky. The radius, the length of the vector is 1 over the wavelength. And then I often talk about angles. In this case, my angle is alpha. And in the small angle approximation, k is alpha over lambda. So we often interchangeably talk about angles and as a function of angle, and we rarely mean momentum. But the lenses are set up and calibrated in terms of angles. There's the forward Fourier transform and the inverse transform, which has the minus sign. I'm hoping you've done a lot on Fourier transforms because we did them in Robbie's lecture and then for a lot of the tomography theory. So I know a lot of you were not comfortable with Fourier transforms at the beginning of the week. How are you feeling now? Not so much that I expect you to do the math, but how they feel like conceptually. Sort of about half-half. Yeah. The physicist types are like, yeah, no problem. We do that in our sleeping for breakfast. So just reminding you a couple of the shapes we're going to jump up about. The important one is if I have a little, here's an aperture, right? This is nothing got through over there, then I cut a hole in the middle and all the electrons got through, and then nothing got through on that side. This shape, this is like a one-dimensional version of our physical aperture in the microscope. And so if I put a physical aperture in the back focal plane, when I go from the back focal plane to the image plane, I did a Fourier transform. Technically, I did an inverse Fourier transform because I did a Fourier transform to get there. So inverse Fourier transform is a sinc function, this oscillating thing. If I did this in 2D, which is more realistic because this is my real aperture, my aperture is all the electrons get through the hole and none of them get through the aperture, which is good. When I Fourier transform this, I get my sombrero function, which is the Airy function. And this function J1 is my Bessel function. And this just looks, well, you can kind of see it's like the 2D version of this guy. The only thing with the Bessel function is the roots are not uniformly spaced. Nevertheless, we remember the first root because that was going to set the, that's basically often how we define the width of this peak, and that was how we set and defined our diffraction limit. The main thing that you remember about Fourier transforms is I go from space to inverse space, so things that were of size A are now of size 1 over A. If my cutoff frequency was k max, my full width half maximum is 1 over k max. So big apertures, small diffraction blur. And that just follows from the math of that. So that's that little reminder down there. Like frequency and time. Robbie put up this example of DNA. And when you look at the diffraction pattern of DNA, you read everything upside down. And so what he's reminding you is the very small spacings in diffraction space are the very big spacings in real space. So the distance along a turn of the helix is this 1 over p, this tiny little spacing over there. And then this big spacing over here is the distance between base pairs. So you read everything backwards. The largest spatial frequencies, the largest wavelengths are near towards the origin. And exactly at the origin is the DC frequency. It's a constant. Now, let's take a look at some atoms. This is the atomic potential of an atom just slicing through the atom, and here we are looking at it in projection. So we've gone the whole atom, just integrated up and folded it down into a slice. And what you'll notice is it's a pretty sharp function. In fact, it keeps going up almost to a singularity. So the shape of the potential most of it is stuck within 0.1 angstroms of the nucleus. The potential of an atom is mostly the nuclear potential plus the electrons, but most of the electrons are core electrons, which are close to the nucleus. So the whole thing looks basically almost like a delta function. And that means when you Fourier transform it, what's its angular distribution? It's spread out over very big angles. Now, it's not perfectly a delta function. It obviously has a finite size. And so if I was to look at the Fourier transform of my potential, let's call it V of Q as a function of Q. And if you're a Diffraction, now I've been unfair to all Paul, but Paul knows this anyhow. Often we call the Fourier transform of the potential the form factor, so we'll call it F of Q. Basically the same thing, Fourier transform, so they call it F. So if I had a pure delta function, the Fourier transform would be completely flat and would be uniform at all spatial frequencies. Because it has a finite size, it drops off a little bit. And that means that if I look at scattering at large angles, it's less likely to happen than at small angles. And eventually I get to big enough angles and it can fall off pretty quickly. To first approximation, if I'm looking at low order scattering, I'm just going to treat that as a constant. And then if I worry about big angles, obviously it's dropped off a lot. But if I treat it as a constant, it's a delta function. Math is easy. So if I think about, well, what happens if I have a periodic crystal and I fire a plane wave into a periodic crystal? Each atom puts out a spherical wave. All those spherical waves start to add up in phase, and therefore you'll find lines of constant phase at particular angles as you go away from the material. So in the far field, very far away, I'm going to look at the Fourier transform of whatever my object is. And the Fourier transform of a periodic array of atoms is a periodic array of diffraction spots. And so over here is an example of what does the Fourier transform look like if I had only 4 atoms. It's periodic, but it's limited, and so the diffraction spots end up being quite broad because 4 atoms is I would expect a width that would be 1/4 of the spacing between the atoms. And then as the object gets bigger and bigger, if it was 10 atoms wide, then the peaks ought to narrow up to being 1/10 of the width of the distance between the peaks. So one of the things you can do with diffraction is if you measure the width of the peak, you'll get an idea of, and go look at 1 over the width, it'll tell you how big the object was. Or it'll tell you how not parallel your beam was if the object gets very big. So the lesson is the diffraction spots only get sharp when you've got a whole bunch of atoms in your object. And the rule of the thumb is if my object was 1 atom wide, the diffraction peak would be as wide as that diffraction peak is. It would be very boring. 4 atoms wide, it's 1/4 of the distance between them, and then 1/10, it's 1 over n basically for the width. And so, by the time I've got a nanoparticle that's 10 atoms across, it's developing a fairly respectable looking diffraction pattern. Just reminding you in general, if I have an object, here's a 2-dimensional object in real space, and it has some spacing d, its Fourier transform is a reciprocal lattice, which is also a series of dots, but the distance between the dots is 1 over d. So the biggest spacings are the smallest dots. And then in 3D, you obviously get a 3D set of dots. And when I start to look for this particular dot would correspond to a set of waves traveling in that direction, which corresponds to a series of planes. So what we've tried to mark out on this thing over here is there's one little unit cell, and then a spot which is a 1, 1, 1 spot would have cut through the diagonals of those 3 things over there. and a 222 spot would have cut through that thing twice before. It has twice the spatial period of the 111 spot. So if I had a 200, actually here's a 220 spacing. They've, no, this one is doing 1, 2, 3 times. So this one they've constructed a 320 spot. And you can see it's got lots and lots of lines inside the unit cell. So the fundamental frequency is like the 100 or something, it's the lowest order spot. And then when I start to see reciprocal lattice spots at higher and higher frequency, they're Fourier coefficients that are oscillating many, many times inside that unit cell. So the 200 spot is going to basically let me describe atoms that are halfway inside the unit cell. A 40 spot lets me describe an atom that's a quarter of the way inside the unit cell. If I want to describe the position of atoms as little delta functions, I need an infinite series of reciprocal lattice spacings. Each lattice spacing is a Fourier coefficient in a Fourier harmonic series and lets me describe the structure with higher and higher spatial resolution. So if I want to form an image that has lots of detail in it, I need a lot of Fourier coefficients in the image. When I pick different crystal structures and I look at those crystals down a particular zone axis, and I want to do that because if I have a crystal and I look at it at a random orientation, then all the atoms aren't lined up one behind the other. And then when I look at it in the electron microscope, it's a mess. So the only way I get to see atoms in an electron microscope is I have to orient my crystal down a zone axis. And high symmetry zone axes give me the largest spacing between the atoms, and therefore those are the easiest ones to resolve. If I had infinite resolution, I could pick an arbitrary zone axis. We tend to work with just the high symmetry zone axes because that's where the atoms are spaced an angstrom apart or more. So if I picked a BCC crystal and I looked at it down particular zone axes, it would give me different diffraction patterns down each zone. And some of those diffraction patterns are not unique. So some of those spots you won't be able to tell if it's BCC or FCC. But if I look at a different zone, then if I look at more than one zone, you can usually tell which it is. So that's something you have to keep in mind. We often have tables that are just generated sample diffraction patterns. So I know if I look down 100, I expect to see a 110 spot and a 020 spot, but I won't see a 100 spot that's forbidden. And the only time I'll see a 100 spot is if I have superlattice ordering within the cell, because it's got lost by constructive interference. Here's FCC and HCP. The problem is if I look down at things like a 111 zone, you can always find on the corner of the cube things that look like hexagonal symmetry. So then that doesn't necessarily mean it's a hexagonal material. It's just I'm looking down something, corner of a cube has that symmetry. Very important concept when I talk about diffraction is called the Avold sphere. And all I've done with this Avold sphere is I've redrawn my scattering diagram over here by taking, there's my initial wave vector, there's my scattered wave vector. I've copied my initial wave vector over there. I've drawn my momentum transfer over there. And now the way to think of this is my incident electron was traveling direction k, and it's allowed to scatter to any point on the sphere k prime. You might say, why is that a sphere? Why am I constrained to scattering on the sphere? Well, I'm talking about elastic scattering here, not inelastic scattering. So this is called on-shell scattering. The elastic scattering, you'll remember, energy for a free electron is p squared over 2m, right? Which is h bar squared k squared over 2m. And that means if the energy before collision is the same as the energy after collision, because I'm not allowing any energy to be transferred to this infinitely heavy nucleus, then if E is the same, p squared is the same, and therefore k must be the same. So for elastic scattering, the length of the wave vector k is the same before scattering as it was after scattering, and therefore any possible allowed scattering event is only allowed to be on this shell. And then the momentum transfer over here, Q, is k minus k prime, and then 2k sine theta. And then you have to watch out for this particular definition. I would have defined this whole thing as theta, and this would be in theta over 2. But this is the physics definition, as you can tell from the annoying 4 pi stuck in the front. The crystallography definition would just be 2 pi over lambda. Now, I'm going to skip this one, but basically all we're going through in a very long discussion here is the only scattering that's allowed to happen is what falls on that sphere. And so I now have a little bit of a constraint, right? Here was my initial scattering. Here's my here's an allowed diffracted wave, for instance. The only scattering events I'm allowed to happen are the ones that happen to intersect the sphere. So when I ask, what do I see in a diffraction pattern? What is the allowed momentum transfer given conservation of energy and momentum? Is only scattering events that are going to interact with my beam are the ones that lie on this Avold sphere. So in this case, it's a very curved sphere. I'm going to get, this is my unscattered beam. It's always going to be bright. This is, I'm going to get one diffraction spot here and another diffraction spot up there and nothing else. So at an arbitrary tilt of the crystal, I don't get to see all the reciprocal lattice spots. My diffraction pattern only has a few dots in it. A little bit of jargon over here. You'll notice that I get diffraction not just in the xy plane in projection, but also in the z direction. And these are called Laue zones. So Zols means zero order Laue zone. That's scattering in the plane, which is kind of most of what we're going to see with electron microscopy. But if I scatter that has a significant change in the kz momentum, this is the first order Laue zone, that's the second order Laue zone, and these are higher order Laue zones or Holtz. So you'll often hear us talking about Holtz lines, and it's not named after Megan. And so let's take a look at a diffraction pattern. What you'll often see is if I'm nicely lined up and everything is well oriented, and this is a big difference between electrons and X-rays. X-rays have tiny baby little wavelengths, which actually means they're actually really big. So they have tiny little K vectors, and so X-rays, the Avold sphere curves up like that, and it means you don't get to see a lot with X-rays. Electrons, the Avold sphere is almost flat, so I get to see a whole bunch of diffraction spots in the zero order Laue zone. That's mostly what you're going to work with. You can see there's a whole bunch over here. So here's an experimental diffraction pattern. There's a whole bunch of spots there. That looks great. That's easy to interpret. It's the stuff down here. Then there's a gap, because over here my Avold sphere does not intersect any of those spots. And now it intersects a bunch of spots. Here's my first order Laue zone, and if I kept going out, there'd be a second order Laue zone out there. So we often refer to these as the Holtz line, even though it's the Foltz line. But maybe we'll save that one for California. Now, if my crystal is tilted, then my Avold sphere is not going to intersect this nice flat thing like this. It's going to look more like something like that, where it's intersecting at a random orientation. And so what you can see here is as we tilt, the Avold sphere cuts through the crystal not centered around the central spot, but it's off to the side. So here is an example of a couple of tilted crystals. And you can see there is my Avold sphere intersecting as a circle, and the pattern is not symmetric. And I think this one is meant to be close to the zone axis. This is close to symmetric, but I'm not entirely happy with the tilting. So our colleague Mark didn't get quite on the zone axis. This one is pretty badly tilted, And often what happens is the way to think about your tilting of the diffraction pattern is remember that this spot, the unscattered beam, is always pinned. And then I'm trying to tilt by moving the Avold sphere so that it ends up going shift, 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 shift. And now it's centered around the central spot. Now I'm on the zone axis. So this is important for 3D crystals. If you attempt this for a 2D crystal, you'll be quite frustrated. And I mention that because I had a postdoc who tried to tilt a 2D crystal and was wondering why it didn't work so well. And here's why, basically. The reciprocal lattice with just the little delta function there is the diffraction spot for an infinite crystal. Now, imagine I had an infinitely large crystal, and I multiplied it by a shape factor. And they have hidden. Okay. I apologize to Paul again. But here's an infinitely large crystal. We know when we Fourier transform this thing, I'm going to get a series of diffraction spots that, if this was spacing A, these are going to be spacing 1 over A apart, infinite series of spots. If I multiply the crystal by a shape factor like that, right, because it's a finite object, it's a nanoparticle, that means in the end I end up with just a whole bunch of dots there. I don't get all the other dots that would have going off to infinity got cut out. So I did this thing, and I multiplied it by the shape factor to give me that. What would happen in reciprocal space to that object? If I multiply things in real space, what happens in reciprocal space? They get convolved. But the Fourier, so if I want to ask what happened to my beautiful diffraction pattern with its nice sharp spots, and I go to Fourier space, I have to convolve the Fourier transform of my lattice with the Fourier transform of my shape. Fourier transform of my shape is this is very wide, so what I get is something that's quite narrow, but it's one of these little sinc function-y things, right? And I have to convolve them, so every one of those dots became a little wiggly object. Like that. So a finite object has a diffraction pattern that has the same periodicity as the infinite crystal, but the shape of every diffraction spot is telling me the shape of the object. And so if I had a cube, I am going to get the Fourier transform of a cube. A disk is, if you think about what happens with a disk, it's fairly wide that way, so its Fourier transform is going to be narrow in this direction, but the disk is narrow in this direction, so it's going to have something very elongated in the vertical direction. If I had a 2D sheet, then it's going to turn itself into an infinitely long rod. So think of the extreme limit of this is going to be my graphene. So what's going to happen with graphene is that each of my diffraction spots is turned into a long rod, and these are reciprocal lattice rods, so we call them REL rods. So what happens if I had a piece of graphene is I have these really long rods, and no matter where I tilt, I still intersect the rod. So I get beautiful looking patterns of graphene even when I'm off by a couple of degrees, because the rods keep intersecting my Avold sphere. So this is just talking about the observed intensity of the shape factor. smaller the object, the bigger the shape factor, the easier it is to see a diffraction spot. So here is, and I apologize to Blanca because she's probably sick of this from Jim Zwo's class. Here is graphene. Here is the Fourier transform of graphene, working out the lattice vectors and the reciprocal lattice vectors. It's a 2D sheet, and therefore I have rods. So this is what my diffraction pattern, this is what my diffraction space looks like. Now I ask what happens when I intersect it with a Avold sphere. And so if I have flat graphene, this is what I'm going to expect to be intersecting. If I have a rough piece of graphene with ripples, then I'm averaging over a whole bunch of pieces of graphene at different tilts. And so what that does is I get a line perpendicular to each surface normal. And because the graphene is rippled, the surface normals form a pattern of cones. And so when you now take a look at graphene, which has thermal fluctuations to it, and you look at it as a function of tilt angle, what happens is the diffraction spot at 0 tilt, the diffraction spot is very small, and at large tilt, the diffraction spot got fatter and fatter and fatter. And so you go and you look at the width of the diffraction spot, it gets bigger with tilt, and in fact, if you measure that, you know the root mean squared distortions and ripples in the graphene. Okay, so now let's get back to thinking about real space again, but not quite yet. Here is a diffraction pattern of a piece of silicon. Right, it's 110 oriented silicon. I'm now going to put in an aperture that only lets me keep these 4 diffraction spots. What is the Fourier transform of a delta function at plus k and minus k? The sine wave. So this image is going to be made up of one sine wave. It could be a cosine because I've only shown you the intensity, and so we don't know the phase on there. But sine or cosine, and all that is it's a sine wave that's been shifted in space. So other than an arbitrary shift, which we lost because I squared things, it's a sine wave. But what this tells me is I have one sine wave running in this direction like that, and I have a second sine wave running in that direction like that. 2 sine waves at 90 degrees to each other. And that's the image, 2 sine waves overlapping. It also happens to be those are the position of the silicon atoms down the 100 zone axis. So the sine wave is peaked at the position of the silicon atoms because this is an annular dark field imaging where the scattering is strongest on the column. So if I take a material and I add some more Fourier coefficients to things, I can build up an image that looks sharper and sharper. So here's the diffraction pattern of graphene. And there's a first ring of spots, and those correspond to a spacing of about 2.7 angstroms, which is the distance across the ring. Then the higher order spots, that's 1.3 angstroms, so that's the spacing inside the bond length of carbon, basically. So this would be an ideal image of graphene. If I let through all of these diffraction spots here, the first ring and the second ring, I get to see the spacing. This spacing here is given by basically that second ring of diffraction spots. And if I take out that second ring of diffraction spots, then you see that spacing goes away. I got rid of that one, and that would have got rid of the spacing that was running from there to there. This spot, those 2 spots give me that spacing over there. And obviously, those spots, that's that spacing down there. So, and with just that first ring, I've got something blurry like that. Now, if I have a blurry image of graphene, that's what it looks like. If things are working nicely, I get to see that. The lesson I want you to do is kind of visually clue in your head when you see spots in a diffraction pattern or an FFT, they just come from a series of sine waves that make up the image. And if I want to have a nice looking image, I need more than one set of sine waves. So when when you're setting up your optics, you want to make sure that you can get enough information into the lens that this kind of diffractogram will pop up. Okay, I covered this one. In the first lecture, I want to go through it again, having talked about diffraction again, because I'm going to ask you a question this time. Right? Here's a piece of graphene. There's the diffraction pattern. I expect it to be a single crystal pattern, but actually when Pin Shane did this, she got a whole bunch of polycrystalline rings. So what I told you about was, okay, let's put an aperture in over here and only let the scattering through at that particular spot, and then do it multiple times to form an image. And to remind you, if I go back a very long way, what did we do? Right? Effectively, we've done this. To form that image, we put an aperture around that little diffraction spot over there and used that to form an image. Now, here's the question. What do you think is the spatial resolution of this image? Is it an atomic resolution image? It can't be an atomic resolution image because I'm not letting all the diffraction spots inside the aperture, right? If you kind of think, now we'll find out how quickly we scroll through this thing. Right? Here's my image of graphene. Here's my diffraction pattern of graphene. To do the dark field image, right? It's not that I know that if I let all of these spots into the aperture, I got this thing. But now I'm going out here, and I'm only taking this tiny little piece here. I obviously couldn't possibly be forming an image with atoms in it anymore. Right? Think about it. This distance from there to there is the momentum transfer, or the Fourier coefficient that I need to produce a sine wave with a lattice spacing of one atom. If I put an aperture around here that is a tenth the size of an atom, what do you think the spatial resolution is going to be? Order of magnitude. So I've selected out a piece of momentum space that allows wave vectors that are a tenth of a wave vector that produces an atom. What do you think the spatial resolution is going to be? The wave vector delta k is a tenth of k0. 10 times. So the aperture size, if it's 10 times smaller than this distance, the resolution is going to be 10 times worse than atomic. So a couple of, maybe a couple of nanometers. So the spatial resolution of this diffraction method is set by the size of the aperture that I put around my diffraction spot. And if I wrote this out as just mark it off over there. It's a coherent imaging method, and I'm using sine theta as approximately theta. So you remember when I told you if I have an aperture, the Fourier transform of the aperture is an airy disk, right? That sombrero function. Well, remember that I picked a very tiny aperture, and therefore I'm going to have a very fat sombrero, and the width of that sombrero is given by this formula over here. So if this thing is, if this is DC, this is 1 over k cutoff. 1 over k cutoff is a tenth, then DC is 10 times. So the dark field imaging method you're going to work with this afternoon has an intrinsic resolution limit, which is it's got to be worse than atomic, and it's probably 10 to 20 times worse than atomic. The sharper and the better the tinier you make your aperture, because you want to get that spot and the one next to it, the smaller you make your aperture, the worse your spatial resolution becomes. Physically, what's happening is my probe in real space is getting fatter and fatter and fatter. And that is just delta k, delta x is a constant. That's your uncertainty principle. If I want to have very, very good momentum resolution, I have to have bad spatial resolution. Well, there's one thing you're going to discover this afternoon that's bad news. Right? The way I've described the experiment is we just took our aperture and we moved it out to this large angle, and I took an image at that large angle. Problem with this is this aperture is now way off the optic axis. Remember, my lens doesn't work well off the optic axis. It has aberrations to it. So the thing to remember is that if I had an ideal lens, all the rays would come back to a focus at this point over here. But if my lens had spherical aberration, then the rays that come in at big angles off the optic axis, which is over here, is bent much too strongly. And so it doesn't come back to the same place. If I had a big object and I took all the rays everywhere, this would be a horrible out-of-focus blur. It's not a complete disaster because my aperture is tiny, so I'm only getting a couple of rays that are all deflected about the same amount. But it has the consequence that this image over here with the aperture shifted off the optic axis is shifted with respect to the image that was formed on the optic axis. So now when I did all of these different images, they're all going to be shifted with respect to each other. So when you look at their images, they're not lined up one on top of the other. You're going to have to shift them by hand. And if you don't know how to do that, then you're in trouble. So this is basically an off-axis dark field image, and it has a few problems to it. So let's look at the ray diagram of the microscope. Bright field image. Here's my objective aperture. It's on the optic axis, so it has no spherical aberration. Here's my diffracted beam. There's my optic axis. There's my direct beam. This is forming my bright field image. My diffracted beam is off the optic axis. This is bad news. So when I go ahead and I put my objective aperture over there to form a dark field image, I'm going to have this image will be shifted with respect to that image. We kind of drew that diagram before on the previous page. So how do I fix this up? The answer is that my diffracted beam must pass through the center of the optic axis in order for it not to be shifted. And the way I make my diffracted beam pass through the center of the optic axis is I have to tilt my illumination. Now, because remember, the scattering angle is the Bragg angle. So the Bragg angle over here is that angle there. It's the same angle. But before I started out tilted, so now I come down straight. Over there I came in straight, and so I get deflected to the side. Now, with the tilted beam illumination, my diffracted beam passes through the center of the optic axis. The result is, if I now work with my aperture always fixed on the optic axis, and instead I tilt the illumination of the sample, then none of my diffracted images move when I move my illumination, when I pick a different diffracted beam. Now all the beams are nicely lined up, and I can stack them one on top of the other and make beautiful color images for nature. I should point out that this whole technique is a really ancient technique. It's been used since the 1950s. And it's sort of been forgotten until about the last decade, because everyone's like, I can take pictures of atoms. Why do I need to do this horrible diffraction stuff? Diffraction's hard. But it's coming back. So centered dark field is, I think, one of the experiments you'll get to do on the one of the microscopes is set up for centered dark field. Every microscope built after 1950 can do this kind of imaging mode. and then you might just have to have some alignment markers in your image to figure out how to line them up. And more modern machines are set up to do centered dark field. The other little ingredient we're missing is the details of the scattering in the angular distribution, the scattering and the multiple scattering of electrons. So the first thing I want to kind of point out is this is the scattering intensity of a single atom at 100 kilovolts for different types of atoms. And what we're doing is I'm just plotting out the amount of signal as a function of atomic number for different integrated ranges of angles. And the thing that I want you to notice is that scattering at high angles means, think of Fourier space. High angles is very short distances. So scattering at high angles is scattering from the nucleus of the atom, Rutherford-like scattering. And so the scattering distribution is a very nice smooth curve. It's basically going to be proportional to z squared, because Rutherford scattering is proportional to z squared. The problem with Rutherford scattering, if you remember your freshman physics, is it doesn't happen very often, so the cross-section is absolutely tiny. 1 part in 10 to the 4 for something like a carbon atom. If I look at the total scattering or the forward scattering, it's a lot more signal, but it doesn't vary smoothly with atomic number. Right? What's happening is it's zigging and zagging because the small angle scattering, you're measuring the mean inner potential of the sample, and that's basically the size of the atom. And if you remember your periodic table, as I go across the periodic table, the atoms shrink in size, and then you go back to the next row and they get big and fat again. So the problem with small angle scattering is some elements actually have very similar scattering contrasts. Carbon, nitrogen, oxygen all look very similar to each other in the forward scattering. This is really bad news for biologists because all they care about are carbon, nitrogen, and oxygen. And then the biologists say, well, you know, the physicists laugh at them and say, well, maybe you should be looking at the high angle scattering, and the biologists say, yeah, I would, except it's so much weaker, I got nothing to look at. I'd rather look at everything that looks the same, but I can at least see it. So that's our challenge in the scattering distribution, is the small angle scattering doesn't have easily interpretable atomic number contrast in the way that the high angle scattering does, but it's a nice strong signal. So TEM, which is looking at forward scattering, you're going to get this contrast curve. Annular dark field STEM, you're going to get that contrast curve. What this means is, when you kind of compare things out there, the TM imaging and bright field phase contrast imaging has a very weak atomic number dependence, and it oscillates, that it's possible that if I picked, you know, this element here, it actually looks lighter than that element there, which actually was a lower Z number. So can be a little confusing at times. The high angle scattering, the angular dark field imaging in STEM, fairly well behaved. It's not quite Z squared because I don't get to big enough angles. But the way to think of this is, if I want to look for a heavy atom in a light matrix, so this is a platinum or a gold catalyst on a carbon support, I use annular dark field STEM mode. If I'm looking for lithium atoms inside a lithium cobalt oxide battery, I probably want to use some phase contrast method, either bright field STEM or annular bright field in the STEM mode as well. And so this is just sort of a reminder of knowing how to pick and choose your modes. Now we get to what happens in thick crystals, right? So everything you've done so far has been, I use my lens to make a wave function, and I convolve that wave function with the sample. And that gives me my object. In a real material, what's going to happen is my wave function is going to change shape as it goes through the sample. And so the resulting signal, I can treat it atom layer by atom layer as a convolution if I want to, but I have to remember that as I go through the sample, I'm convolving with a different object because my probe is being focused by the sample, right? My My electrons are negative. My sample has all these positive nuclei. Think of the positive nuclei as acting like a little lens or a fiber optic cable that focuses my beam onto the column of the atoms and causes it to change its shape. And this is often, you can solve the problem with Bloch waves in a periodic crystal, but often we do it numerically by a simulation method called multi-slice. So the first kind of approximation we often make is called the strong phase approximation, where I'm going to look not at the square of the wave function, but the wave function itself. So I start out with my initial wave function. I multiply it by a transmission function. In optics, this is called the phase grading approximation. And then I end up with my final wave function. And in fact, you can simplify down Schrodinger's equation. And if you don't allow the wave to propagate, this is what it'll end up looking like. So this is the first approximation. The strong phase approximation says that the transmission function is e to the I sigma v. V is the potential that I'm scattering from, and all that the potential does is introduce a phase shift, and sigma is a coupling parameter that describes how strongly the electron beam is going to interact with the Coulomb potential. It's just a function of beam energy. This is, by the way, if you think about it, it's just the WKB approximation. If you go back and remember your undergrad quantum mechanics. Now, what this has the effect of doing is, because this is a projected potential, is I started out with a real object, and the strong phase approximation has done this to the object. Now, there are times where this is a good approximation, but obviously for 3D objects, this is not a good approximation. So what the strong phase approximation assumes is that the probe shape didn't change. Why? Because all I did was change the phase, and the shape of the thing is psi squared, and e to the I sigma v squared is just 1. And the second thing is the strong phase approximation doesn't allow for the beam to change and propagate in distance. So the strong phase approximation is going to work when my sample is thinner than the depth of field of the beam. And it's going to work when I don't have such strong scattering that the probe changed shape. So under those two conditions, that my sample is thinner than the depth of field and it not having insanely heavy elements in it, it's a good approximation. Strong phase approximation works for a single atom. So what we do in a real sample is we take our sample and we break it up into a whole bunch of very, very narrow slices, and we apply the strong phase approximation in every slice. There it is. We then apply a propagator, that's our Green's function, and we convolve the propagator with that slice, and that then let me move, let the beam spread, let the scattering happen, and then I iterate again and apply it on the next slice. So here's my transmission function, which is just WKB, and the multi-slice code has sliced my potential up into thin slices, and then here I am. The transmission function is the transmit step, which is this multiplication. Then I propagate. The propagation is a convolution. If you're thinking quickly, you'll realize that the quick way to do a convolution is to Fourier transform and multiply. Then you inverse Fourier transform back. And now I've propagated my beam from this slice to that slice. Then I introduce another transmission function and another propagator. So I basically apply this algorithm iteratively at each slice throughout the crystal. You want one slice for every row of atoms. Don't try to take shortcuts because you'll miss the Holtz lines. And at the end of it, you'll have propagated the beam through the crystal. This, by the way, is a discrete approximation to Schrodinger's equation, which is pretty good down to about 20 kilovolts. Why am I telling you this? Remember on Sunday afternoon, you used a code called Computem. This is the Computem algorithm. So if you go to Computem, it has a whole bunch of, when you say run, and it had a whole bunch of image modes that you could run. IncoStem is basically the strong phase approximation. And then if you say multi-slice or stem or TEM or any of the other modes, it's running the multi-slice algorithm. And then we gave you a link to a nice set of instructions for CompuTem and a little tutorial for that as well. So what I'm going to do now is I'm going to use CompuTem, or a slightly more sophisticated version, to show you what happens to an electron beam as it goes through the crystal. So here's a very quick example. Here is a single column of titanium atoms, nothing else. The beam starts out being placed next to the titanium column. So here, let's wait for it to clock around, and it'll eventually tell us when it starts at 0. You'll see the beam beginning from the beginning. Let's wait. OK. I'm going to restart that, so you'll watch it run again. There we go. So the beam started out there. Very quickly, what happened is it got sucked onto the titanium column, and now it's bouncing back and forth. We're going to look at this in some more detail. I just want to show you that the beam does change shape and is very strongly affected by the crystal potential. So the convolution gets complicated. This is a simulation that Celesta did. She's showing you over here the strong phase approximation. Would have predicted how far the beam moved, would have been that curve. And in fact, if you do the multi-slice, it follows this beautiful oscillation. So what you see is the strong phase approximation breaks down about there, fairly thin into the sample. What she's actually measuring here is something we're going to talk about in the next lecture, which is the differential phase contrast imaging. This is actually center of mass imaging. Here's another example. Here is silicon. So it's 110 silicon, and there are 2 columns of silicon atoms marked out over here. I put a probe incident probe onto the silicon column over here, and very quickly the electron beam is sucked and changes its shape. Basically all that's happening, if you think about it, is I have a row of positive charges like that, and a big fat electron beam is very quickly reshaped and attracted to the column. So it gets channeled onto the column. Think of the column as like it's a deep potential. It's like a little fiber optic waveguide, and my electron beam is sucked into that fiber optic waveguide. There's another little waveguide sitting next to it. That's the second column of atoms. So there's a little bit of exponential leakage from this wave function to the next one. And you'll notice after a while, the electrons have now leaked onto the neighboring column, and there they are, and they're building up quite a bit of intensity on the neighboring column. So here's a plot of the intensity on the first column. This is from a paper. In fact, the first author is Paul Voiles, who some of you know, and it's from 2002. So if you Google Muller and Voiles, you'll find it. So what we're showing over here is the angular dark field image intensity, which is scattering close to the nucleus, is basically look at the intensity of the beam on the column, and then this is the intensity of scattering from the first column. Here's the scattering from the neighboring column. Sum those two up, and you get the image intensity in the angular dark field image. Here's another example. In free space, with an aberration corrector, this is what I'd expect my beam to do. It's focused on the top surface, and now it's blurred out. Here's the funny thing. If I put one column of atoms in, then what happens is the beam channels down that column of atoms, and it remains focused on the atom column actually quite deep into the sample. And that's actually a good thing for imaging. It makes it easier to image thick samples than you would have expected otherwise. If I have a neighboring column right next to it, which is what happens in silicon, then the electron beam actually hops to the neighboring column and back again. It beats. And if you go read this paper, you'll find out the atomic physics that explains that analytically. Basically, I've formed bound states. I have, think of my propagation in time, propagation in distance as an evolution in time because it's traveling at constant velocity. And I've basically solved Schrodinger's equation for a time-varying 2D potential. Well, it's a static potential. I'm just solving it in time-varying. And it's now 2 atoms, and I'm forming molecular orbitals with bonding and anti-bonding states. And I'm just beating between the bonding and the anti-bonding states. And that's the analytic model, which describes the multi-slice quite nicely. This has some consequences that we've got to be careful of. When you're trying to image dopant atoms, for instance. So here is, I have two silicon atom columns over here and here, and I have put a dopant atom on the first column but not the second. And then if I look at if I look at my image without the dopant atom is bismuth, it looks like a little dumbbell. If I put my bismuth atom on the first column where the sample is thin, then that column is extra bright, and I go, aha, I have a dopant atom here. I just imaged a dopant atom in my crystal. But remember how the column beats back and forth? So imagine if I put my dopant atom over there, you'd never see it because the electron wave function never touched there. And if I put my dopant atom there, you'd say, hey, I have a dopant atom on this column because I put my beam over there, even though the wave function ended up there. And so that's what's happened over here. Over here, the bismuth atom is invisible because it's at a point where the wave function wasn't. Over here, the bismuth atom was far enough down that it was basically over there. And so now, when I put the beam on column 1, it doesn't show up. But if I put the beam on column 2, it channeled over to column 1 and it lit up. So now the bismuth atom appeared on the wrong column because of channeling. So the lesson is, if I'm looking at dopant atoms, I either need very, very thin samples, or I need to do my multi-slice simulation to figure out what's going on. But people, particularly at some of the national labs, were not very good at sample prep and tried to count dopant atoms and got it all horribly wrong. We just made very thin samples. These channeling effects have other implications. They change the shape of the probe, and it affects the quality and the resolution of the image. So the apparent distance between the dumbbell spacing and the silicon is actually a function of sample thickness and how big an aperture you used in the microscope. So if the sample is thick, you can't always read off the positions very precisely and trust them. If the sample is thin, it's pretty robust. Thick in these cases is actually fairly thick. Usually the images don't look that good when they're thick. So the thing I'd say is if you're trying to measure atomic positions with high precision, you want really nice looking images. If the images look a little bit fuzzy, there may be channeling artifacts in them. You can always check it by running the multi-slice simulation. That's what it's for, right? If you want to know, could my atom position have shifted, run multi-slice and see whether that's the case. The channeling has a very nice property to it that I should kind of point out generically. Look how most of your scattering happened in the first 20 nanometers of the sample. So what that means is most of your scattering happened where your beam was focused. And when your beam wasn't focused, it didn't do a lot of scattering either. So the result is I can look at very, very thick samples. Here is something that is 300 nanometers thick, and it still has a respectable looking lattice image. Here it is 600 nanometers thick, and you can still almost see the lattice image. And everything, all that's happened is the contrast has got horrible because the part of the image that was giving me contrast was like the first 30 nanometers. So this one already would look nicer if I was a little bit thinner. But that's kind of one of the nice things about dark field imaging. Your contrast depends on the angle that you scattered to. And scattering at small angles is very sensitive to disorder in materials and displacement off an atom column. And so if you have two simultaneous detectors, you can learn a lot about the depth, how far into the sample your dopant is, and how far off the atom column the dopant is. So we did this back in 2003, and about a decade later, Suzanne Stemmer picked it up and redid the same thing again and used it for measuring dopants in different materials. We were looking at silicon, and she looked at strontium titanate and oxides. The other thing you have to kind of be aware of is if you're one of the easiest, there are two ways to get a lousy looking STEM image. One is your sample is too thick, and you want a really thin sample. The thinner the sample, the better your STEM image. The other way you get a bad STEM image is your sample is tilted. Now what usually happens with people is very thin parts of the sample are badly tilted. So people go to a thicker part of the sample because they can get on the zone axis. But then it's thick. So the problem is you've got to get two things right. You've got to get thin part of the sample, and you've got to get the thin part of the sample on zone axis, and that's a pain. It takes a long time to do that. But if you're in a thin part of the sample and it's tilted, your contrast drops quite quickly. So this is just strontium titanate. If you're tilted by more than a few milliradians, if you're tilted by under a couple of milliradians, there's no impact on contrast. It's pretty forgiving. But once you tilt more than a few milliradians, your contrast starts to drop. And then when it's like mistilted by 2 degrees, the contrast is absolutely terrible. So this is why you want to look at your diffraction pattern and make sure it's perfectly symmetric, because if it's not, you just killed your contrast and you got a lousy looking image. And then how your contrast varies with tilt depends on whether I'm looking at small angle or big angle scattering. So I think that's all I want to say about scattering in thick samples. The main thing as a practical detail is don't work with thick samples. And then people end up working with thick samples because they're having trouble tilting on the zone axis. It's better to be a little bit more patient and get yourself on the zone axis in a thin part of the sample. If you do that, life is easy. If you don't do that, you're going to have to learn how to use multi-slice. That's the main lesson I wanted to make. If you want to understand how to do multi-slice simulations, Earl Kirkland's book is the book to read. It's basically an instruction manual for the multi-slice code, but it has all the theory in it as well. A very simple bedtime reading version of microscopy is the Williams and Carter textbook. It's intended for undergraduates with basically someone with a background who has basically a sophomore level materials scientist. But what that means is it's very easy to read and you don't have to think very hard because he's not going to use any math or anything like that. But it gives you a nice picture of stuff and it points you in the right direction. If you want to understand diffraction in great detail, John Cowley's is sort of the classic book. It's pretty old because he's no longer alive, so he can't update it. But it's very, very clearly laid out. There are more modern books, but they're not as easy to read. And if you're looking for other ones, I can recommend more modern ones as well. So that's the main thing I want to talk about in this lecture. We'll come back after the break, and we'll get started on detectors and pixel array detectors. So a little understanding some of the jargon about what makes a good detector, and then what happens when I can measure in real space and reciprocal space together.